We were discussing the magnetic field produced by a solenoid. We have said something about the direction of the magnetic field by using the ideas that we get from Biot-Savart law. But we can get some of the same results by using the symmetry, in that problem too. So this solenoid symmetry is actually a symmetry kind that is special to the magnetic field problems. We don't have an analog of this thing for the electric field case. So let's just describe what the symmetry is. First, we have some certain axis in here. So there's a certain direction in here. It's not a line, but a direction, basically. So there's this symmetry is the translational symmetry along the axis. Along axis. So that's the only symmetry. So there is no rotational symmetry or any other kind of symmetry. There's one other thing. So the current is perpendicular to the axis. So current is flowing in a direction perpendicular to the axis. Direction, right? Let's just remember what that means. Basically, translational symmetry means that I can take that solenoid and translate it along the direction of the axis, and I get the same physical picture, right? Since the solenoid is really infinite, so it's extending from minus infinity on the right to plus infinity on the left or whatever. In that case, if I translate along that direction, I still get the same physical picture, which means if I have a magnetic field in here, let me show this with an angle. Let's say that the magnetic field in here is, let's say, B1. Then, by translating this point in this direction, I can get a different point. I can reach to a different point. But the symmetry implies that since the physical, the current distribution does not change, the magnetic field at that point should also be the same, because I'm just translating this vector to that point, right? So the translational symmetry essentially tells us that the magnetic field at these 2 points are the same. So in that case, probably it's better to use some kind of an idea of some. Let's just say that suppose there's a certain axis in here, a line that is, right, an axis in there. I can perhaps describe the location of that point with respect to that axis. So in that case, I can perhaps describe the radial distance in here. So as a result, in that case, these 2 points are points with the same radial distance, at least from that point of view. So we are saying that, of course, because of the symmetry, they should have the same magnetic field. Next, can the magnetic field make an angle like that? Can it make an angle like this? So in that case, probably you will see that if that's possible, then therefore some points in here would be making angles in the other direction as well, which then implies that if I think about, just remember the Gauss law for magnetic fields. It was saying that there are no magnetic monopoles, magnetic charges, so therefore the flux integral over a closed surface should be equal to 0. But if the magnetic field had a really component like that along this direction, in that case, you would obtain a non-zero magnetic flux, which will violate the principle that we have accepted, that there are no magnetic charges. At least there are no known magnetic charges in space around us. So as a result, the magnetic field at these 2 points should always be parallel to the axis. Perhaps to the right or to the left. I'm just going to show them to the left, but that's basically by using the Gauss law for magnetic fields, I can say that the direction of the magnetic field should also be parallel, should always be parallel to that axis direction. Right, so it should be the same for all side points as well. So all side magnetic field should also be parallel because of the same reasons. So then there's this next thing in here. So we have said something about the directions, but what about the magnitude? So as a result, just consider 2 points inside. One is at a distance r1 from the axis, and the other one is at a distance r2 from the axis, let's say. And is it possible that these 2 points have different magnitudes? Right, let me just draw this with a longer arrow. Right, that's one of the questions that we are going to answer eventually, but let's just state that by using the symmetry argument, we cannot say anything about this question in here. So as a result, by using the symmetry alone, we can say that the magnetic field in here is parallel to the axis. That's for sure. But we cannot say whether the magnitude of the magnetic field there is the same as the magnitude of the magnetic field in here. Right? So that's not the thing that we are saying. So as a result, if I summarize, let's just think about it like this. I'm just going to just draw a set of points in here. So let's just choose a point in here and some other point in here, some other point in here, and so on. And so as a result, I'm going to also choose some set of points in here at some other place on the solenoid. But let's say that they are just obtained by a simple translation of this set of points. So as a result, what we are saying in here is that when we draw the magnetic field lines, they are always parallel to the axis. They might have different magnitudes. So in here, for example, the magnetic field is like that, let's say, and perhaps in here it's opposite in direction, I don't know. In that case, all of these points, corresponding points in here, should have the same magnetic field in same magnitude and same direction. But of course, different points may have magnetic fields in different directions. So by using the symmetry argument, this is what we can say. Now, because of the symmetry argument, now we can also use the Ampere's law, because in the case of Ampere's law, we actually need a set of points where I can really know the strength of the magnetic field, right? So as a result, after that point, I'm going to start using the Ampere's law. But in the case of Ampere's law, I'm going to do it like this. So let me just discuss it in here. So I'm going to use actually 4 steps. So in the first step, by using Ampere's law, I'm going to show that all the magnetic fields inside are equal in magnitude. So the magnetic field is really uniform inside. In the second step, I'm going to show that the magnetic fields outside is also uniform. In the third step, I'm going to show that the magnetic field outside is equal to 0. And in the fourth step, I'm going to compute the magnitude of the magnetic field inside. Right? That's essentially the steps that we need to take. But of course, there's a logical reason why we follow the steps like that, because somehow I need to start with that first step. Right? So let's then show that any 2 points inside has the same magnetic field. So let's just consider a point in here and some other point in here, right? Let's say that the magnetic field in here is B1 and the magnetic field in here is B2. How can I show that they are equal to each other? Simple. I just need to choose an Amperian loop like that. In the shape of a rectangle, there should be a direction on the Amperian loop. So I just choose them like this. What else? I need to also specify the size of the Amperian loop. So as a result, I introduce this length in here. I'm going to call this long side as length d. This is an arbitrary number that I have just introduced. Obviously, the magnetic field should not depend on the how I introduce this thing. So as a result, at the end of the calculation, this symbol should disappear from our equations. But right now, I need to set a value for this. This side length is also somehow should be set, but since it doesn't enter into calculations, I don't do anything with it. So let's just write down the Ampere's law. So the line integral over this Amperian loop is equal to mu0 times I enclosed. Let's start with the right hand side because this is the simplest. There is no enclosed current in here. There is no wire that crosses the rectangular area enclosed by that loop. So that's clearly zero. So therefore somehow the integral on the left hand side should also be zero as well. All right. To find the integral, I just do a logical division of the rectangular loop. So it has four sides. So as a result, I just evaluate the integrals on the sides separately. So I'm going to call this side as 1, this side as 2. This is third side, that's fourth side. So as a result, I can express this integral as an integral over the side 1 of b dot dl, and there's an integral over the side 2, and so on. Let me not write everything down. And somehow Ampere's law tells us that the sum of all of these should be equal to 0. All right. So the only thing that we know in here is that these are the things that we know. So on side 4, on this side, all the magnetic fields have the magnitude of B2, and it is directed towards the left. On the other long side, all the magnetic fields have magnitude B1, and they are directed towards left. We are going to show that these are equal to each other, so that's our purpose. On these short sides, I don't know the magnitude of the magnetic field, but I know that they are perpendicular to the side, and similarly on side 3. So since this short side is the simplest, I'm going to start from there, right? So let's just do this in a separate page. All right, I'm just going to show this long side in here and then show the magnetic fields in here. So perhaps they have different magnitudes. I know something about the directions as well, so all of these are perpendicular to the line. Let's remember that what we do when we are evaluating the line integral, we just take a small displacement on that line, so we just call this as dl, and then take the dot product of this thing with the magnetic field. So as a result, in here, if you just compute this b dot dl expression, this is equal to the magnitude of the magnetic field, the length of the displacement, multiplied with the cosine of the angle between them. And that angle is 90 degrees now. And since that cosine is equal to 0, that b dot dl is equal to 0. So it is basically the integrand which is 0. It's not just the integral, but the integrand itself. So as a result, if you just integrate the integral of, if you integrate 0, you get 0. Right? This tells you that this first term in here is equal to 0. Right? So the line integral coming from this short edge is equal to 0. And the same, for the same reason, the line integral over this other short edge, this third side, that is also equal to 0. Right? So as a result, we are left with the side 2, this integral, and that integral. So they are going to be non-zero. So I'm also going to compute them. So let me then start with the side. Let me start with side 4. Right? So I'm going to pass to the other page again. So let me erase everything in here. Erase. Let me draw this side, so the direction is towards left, and the magnetic field in here is, I think I have called this as B2, but let me check. Yes, B2. It is the same, right? It's always the same at every point, and so therefore it has the same magnitude and direction. Let's see. So when we evaluate the line integral, of course, we again take the displacement. So displacement is towards left now. It's in the same direction as the direction that I have shown with B2. So therefore, for that case, let me write it in here. So this is B dot dl. In that case, this is equal to the strength of the magnetic field, which is B2. The size of the length of the displacement, this is dl. And the cosine of the angle between them, but that angle is 0, and cosine of 0 is 1. So therefore, this is B2 dl. So therefore, on that side, on side 4, B dot dl integral is the integral of B2 times dl. Since B2 is constant, I can take it out. So therefore, this is the length of that segment. And I have said that this long length of the long side has the length d. So therefore, we get B2d from this integral. All right, let's come back. So therefore, this integral is equal to B2d. Now then, let's compute this integral. So I'm going to use the same picture again. Let me erase everything. Let me draw everything again. So this time the Amperian loop is directed towards right. Magnetic field, I just called the to the left component as B1. So the displacement is, of course, is to the right. So it's a vector like that. This is a dl vector. And so therefore, B dot dl in that case is equal to the strength of the magnetic field, B1, magnitude of the displacement dl, cosine of the angle between them, that's 180 degrees, and cosine of 180 degrees is -1, so therefore this is equal to minus B1 times dl. Right, there's a minus sign coming from the dot product, and so therefore B dot dl integral over that side, this was side 2, is therefore is equal to minus B1 times d. So there's a minus sign coming from there. All right. So as a result, that final integral is equal to minus B1d. So therefore we have 0 is the first term, minus B1d, 0, and plus B2d. All right, let me erase everything in here and then write them down on that picture. Let me also erase everything in here. So this is as simple as this picture. So to repeat, in the line integral of the magnetic field, this side and that side, they don't contribute because the magnetic field is perpendicular to the displacement on that segment of the loop. So as a result, we get zeros from there. So therefore, I don't write them. So on this side, the integral is plus b to d. On the other side, the integral is minus b1d. Why minus? Because the displacement and the magnetic field are in opposite directions. I don't write the zeros. So on the right-hand side, I have 0. You can see that d cancels. So therefore, b1 is equal to b2. So that's the important result, which shows that the magnetic field is uniform inside. B is uniform inside, which means all the magnetic field vectors inside have the same magnitude and same direction everywhere. So it doesn't matter whether the point is very close to the wires or very close to the center. Every point should have the same magnetic field. So I'm going to call this magnetic field as B in, the magnetic field inside. All right. So this was the first step. So in the second step, I need to show that the magnetic field outside is zero. Outside is uniform too. So I'm just going to do the same thing again. So I'm going to take 2 points in here, B1 and B2, and show them that they have the same magnitude. To be able to do this, I choose a similar kind of a rectangular loop as the Amperian loop. This side length is D again. So it's the same argument. There's no difference in here. So probably I don't even have to repeat these. But again, the enclosed charge is equal to 0. The loop integral is equal to B2D from that side and minus B1D from the other side. And we get zeros coming from these two sides, so therefore we get this. So therefore this tells you that B1 is equal to B2, so therefore the magnetic field is uniform outside. So I'm going to call this as B out. Right? So this tells you that the magnetic field outside is uniform. So outside magnetic field is uniform. So that's our second conclusion. So inside and outside, therefore, in short, of a solenoid, the magnetic field should be uniform. Now, in the third step, we have to argue that the magnetic field is zero outside. So I have just shown that it is uniform, but we can also argue that it is zero. The reason is that the method that I use for showing this is going to infinity. Right? If you just go to infinity, when you are infinitely far away from the wire, let's say it like this. When you take the limit of the magnetic field when the point goes to infinity, should be equal to 0, right? Let's say it like this: as you go to infinity. As you go to infinity, the magnetic field should tend to 0. So that's a physical argument, actually. So when you are too far away from the solenoid should have no effect on you. And so therefore the magnetic field at infinity should be 0. So that's a very physical, it's a nice physical argument. But now I just combine this argument with the argument that the magnetic field is uniform outside. So therefore the magnetic field should have the same value at infinity as well. By just combining these two, then we can show that the outside magnetic field is equal to 0. That's not a very clean proof, actually. It's not very clean, but that's one way of actually showing it. So otherwise, if you want a much more exact proof, then you have to go over the Biot-Savart law and then show that the integral is equal to 0 outside. But this is the best thing that we can do. Right? So we just combine this physical idea that the magnetic field should be 0 at infinity with this uniformity proof, and then by just combining these two, we just show that the outside magnetic field is equal to 0. So therefore, what we have is just an inside magnetic field. Right? Let's then pass to this other picture. So as a result, inside the magnetic field is uniform. I just call this as B in. Outside, the magnetic field is 0. So in the fourth step, I just compute the value of the inside magnetic field. How do we do this? Again, by choosing an Amperian loop. Like that. So I'm going to choose it like that, and I'm going to choose the direction of the Amperian loop in the same way. And let me also show the side length, right? This side length is equal to d. Again, d should disappear somehow from our final expressions, so we are going to see that this is the case. So as a result, what we are going to do is we are going to write down the Ampere's law for that case. So let me do this in a separate page because I may need some space. So let's just write down the Ampere's law in the original form. All right. So let's start with the right-hand side. What's the enclosed current in here? You can see that there is an enclosed current in that case because there are these wires, right? These wires in here, these wires, they are actually crossing this surface, rectangularly shaped surface that's enclosed by my Amperian loop. So they are enclosed. So I also see that they are, each one of them is carrying a current I. So as a result, I need to count the number of wires in there. But that's also simple. Let me just say it like this. Number of wires is equal to, we have the turns density, number of turns per unit length, multiplied with the length. That will give me the number of coils or the number of turns that actually crosses that surface in here. So therefore this ND is that number. If I multiply this with the current, then I get the total enclosed current. All right, let's just write this thing down. So therefore the right-hand side is ND is the number of wires, and each wire carries a current I. So therefore this is that. Oh, there's one more thing. I need to decide on the sign in here. Let's go back and look at the sign. So we can see that in the Amperian loop, for example, let me shade this enclosed surface in here. So that's the enclosed surface. We know that this enclosed surface should have an area vector associated with it, and we just choose this consistently with the direction on the Amperian loop. So in that case, this area vector is pointing out of the screen. It's pointing towards us. But the currents are carrying the wires are carrying the current into the screen direction. Therefore, these currents should be counted as negative. Right. So therefore, I put a minus sign in here. I put a white minus sign. All right. So what does that minus sign mean? Well, it means that I didn't plan ahead when I chose the direction on the Amperian loop. That's essentially what it means. So as a result, when I'm computing this b.dl integral, I'm also going to get a minus sign somehow, and these two minus signs cancel each other. So if I have chosen the direction on the Amperian loop in the other direction, I would have gotten a positive sign in here, but it would not change the final result in any case. Okay, so let me then erase all these red signs and these currents as well, so I don't need them anymore. So what I need now is the line integral of the magnetic field. Let's see how this appears. So I can see that since the magnetic field outside is 0, there is no line integral contribution coming from that side, as well as these two sides. B out is equal to 0, right? So therefore these two sides do not contribute anything, so this is equal to 0. So that means there's a contribution coming from this short side, this long edge, and that short side. But of course, these two short sides do not have any contribution because the magnetic field is perpendicular to the displacement, so therefore they don't have any contribution. So we just forget about these two. Right, so as a result, the only non-zero contribution coming to the line integral is coming from this edge in here. And in that case, you can see that the I just need to multiply the magnetic field with the length of the that side. But since the magnetic field and the displacement on the side is opposite to each other, I also have a minus sign coming from there. So let me erase these two, pass to the other screen, and then say that the integral in here is equal to minus b in times d. So the minus signs cancel. That's nice. The d symbol I have just introduced in the middle of the problem, so they also cancel. That's a nice thing because it shouldn't appear on the final result. So therefore the final magnetic field inside is equal to mu0 Ni. So this is the magnetic field formula for a solenoid. So that's a nice formula. We are going to use them a lot in the coming picture. So let's just repeat the argument again in here. So therefore, inside a solenoid, the magnetic field is uniform and has a magnitude given by mu0 times n times I. Outside magnetic field is equal to 0. Right? Let's also say why this is relevant. This formula is relevant. Right? So mu0 is always a coupling constant in a way. It tells us how a current produces, how strong a magnetic field it produces. So it's a fundamental constant of nature. So all of these formulas should involve this permeability quantity, obviously. Of course, the magnetic field is proportional to the current. So therefore, that's not a surprising thing too. And the turn density also appears in here. So it appears that if the turn density is higher, if the number of wires per unit length is higher, in that case you would produce a greater magnetic field. That's also by experience that's the case, and that's why you are using these kind of coils usually with large number density of turns, because you would like to obtain a strong magnetic field. So as a result, every expression in here makes sense. Let's remember again that the cross-sectional shape of the solenoid never entered into the argument. So this can be anything. This can be rectangular in shape to, I don't know, perhaps pentagonal as well, or some other strange shape too. That's not going to change anything. The inside magnetic field will still be uniform, and it's going to have this shape, this magnitude. Finally, let me just say something about this real solenoid. So in that case, we have a finite number of turns and finite length. And so in that case, we have a picture where, of course, the inside magnetic field is not uniform, but we are making this approximation that, I mean, if the infinite solenoid approximation is valid, in that case, the inside magnetic field is approximately, therefore, is equal to mu0 times the number of turns divided by the total length of the solenoid multiplied with the current. Let me also show the current in here. Let's remember this argument again. So if the size, the length scale that shows the cross-sectional shape in here, right? If this is much smaller than the length, in that case, only in that case we can make this approximation. Otherwise, the inside magnetic field would be entirely non-uniform, and it would be far away from this value. But only in that case, we can approximately say that the magnetic field is like that. So in that case too, the outside magnetic field is not 0. But we can approximately say that the outside magnetic field is almost equal to 0. So there is always these fringe magnetic fields that leak outside. That's always the case. But as long as this infinite solenoid approximation, this thing is valid, we can neglect the outside magnetic field, and we can assume that the inside magnetic field is almost uniform.